Hello, welcome back to Statistics and Mathematics YouTube channel. Today I'm going to continue our series of video on probability theorem, specifically that is the moment generating function, and we are going to continue from where we ended the last time. I promised you the last time that we are going to tackle what is termed as what the uniqueness theorem. So what is termed as what the uniqueness theorem? Corresponding to each moment generating function, m of t, there is a unique distribution function having that mt as what a moment generating function. So the theorem means that the moment generating function of a random variable is unique and completely determines the distribution of the random variables, right? And then independency also exists under moment generating function, specifically the uniqueness theorem. And then it's saying that let x1, x2, to xn be independent random variable with moment generating function, right? And we are trying to say that if our y, right, we are saying that if our y is equal to the summation of the independent random variable with moment generating function. So we are going to say that our y is going to sum x1 plus x2 plus xn. Then our moment generating function for y here, the moment generating function for the y is going to the multiplication of the moment generating function for x1, moment generating function for x2, moment generating function for x3 times moment generating function to xn, right? So that is what the independency theorem under the uniqueness field, right? Yes, so let's solve examples to better our understanding on the explanation that I have here. So here we are saying that the random variable x and y are independent with respect to moment generating functions, right? M sub x, right, which is equal to p times e raised to the power t plus q all raised to the power n, and the moment generating function of y, where we are getting p times e raised to the power t plus q all raised to the power n, where we are saying that our p plus q is equal to y. Find the moment generating function of x plus y. And then we just learned that if we are summing, if you have two random variables and we are summing them, right, each moment generating function, we are going to multiply the moment generating function for both the random variable x and then y. So for this question, you are going to multiply the moment generating function for x plus y. So here when we come here, we are saying since x and y are independent, right, the moment generating function for the random variable x plus y is equal to the moment generating function of x times moment generating function for y. And we know the moment generating function for x was p times e raised to the power t plus q all raised to the power n times p times e raised to the power t plus q all raised to the power m. And then since they are having the same base, we are going to add the exponent. So let's go to the working sheet to solve more examples to better our understanding under the uniqueness theorem. So for this question, we are saying that x and y are independent random variable with respective moment generating function. The moment generating function for x is given as e raised to the power 3 bracket open e raised to the power t minus 1, and moment generating function for y is equal to e raised to the power 2 times e raised to the power t minus 1, right? We have been asked to find the moment generating function of x plus y, right? So since we are adding the random variable, we are just going to multiply each moment. So we are going to multiply the moment, right? So sorry, here is supposed to be multiplication, right? Let me correct myself. Yes, here is supposed to be multiplication, right? Yes, so we are going to multiply the moment generating function for both x and y, and here we are going to have e raised to the power this times e raised to the power that, right? And since they are having the same base, we are going to add the exponent, and when you add the exponent, you are going to get e raised to the power 5 bracket open e raised to the power t minus 1. So that is the solution to the first one. We have been asked to calculate for the expectation of x plus y. And since both x and y is independent, the expectation of x plus y can also be split into two. We can calculate for the expectation of x and then add it to expectation of y, right? So when we come here, since we have the moment generating function for both x and then y, right? When we take the first derivative of the moment generating function for x, we are going to get the expectation for x, right? And then we take, after taking the derivative, we are going to put t is equal to 0 to get what? The expectation of x, right? And then for the expectation for y, we are going to also find the first derivative for the moment generating function for y, and then put our t is equal to what? 0 to get the expectation for what? Our y. So once we get the expectation for y and then x, we just add them, right? So here, this is what we are trying to say here. So when you take the function, right, this is what the moment generating function for the x, right? So we are going to take the first derivative, right? And we know that we have this function here. Let me work it for you to understand. We have this function e raised to the power 3 e raised to the power t minus 1. If you are differentiating this one, right, you are going to take the exponent, differentiate it, and multiply by the whole function. So if you differentiate this one, right, if you differentiate up this function, you are going to get 3e raised to the power t. Once it differentiates 3 here, because multiply to once differentiate 3, you are going to get 0. And multiply it by the whole function, you are going to get e raised to the power 3 e raised to the power t minus 1, right? And then you are going to put t is equal to, once you put t is equal to, you are going to get your final answer to be 3, right? So the first expectation of x is what? 3, and the expectation for y, will follow the same procedure. You are going to get 2 here. So you are going to take the first derivative of the moment generation function for y, and then put t is equal to 0, and you are going to get what? 2. So the expectation of x plus y is going to give us what? 2 plus 3, of which our final answer is what? 5, right? Let's solve more examples. This examples, example 2, and then our next question is not basically on the uniqueness theorem, but I want us to solve more questions under the moment generating function for us to better our understand. Okay, yes. So here, consider the random variable x with a probability mass function given by 1 over 5 bracket open x minus 3 raised to the power 2, where our x is equal to 3, 4, and what? 5. And we have been asked to find the moment generating function of what? X. And then we just learned in our previous video that if we are asked to find the moment generating function for a discrete case, right? Yes, we are going to get, you see, since the function was given as probability mass function, that is what? Discrete random variable. Our x is being treated as what? Discrete random variable. So the moment generating function for that discrete case will be summation of our x moving from 0 to what? Infinity of e raised to the power t of x times f of x, right? And then we know that our x is moving from 3 and then it's ending at what? 5, right? So here we are going to get summation of what? Our x moving from what? 3 to what? 5 e raised to the power t of x times f of x, and our f of x is what? 1 over 5 bracket open x minus 3 all squared, right? That is what we are going to what? Get. In fact, that is what I have been able to write here. Okay, then all that you are going to do is to expand it, right? We are going to expand this one. So you see that we have our x is equal to 3, our x is equal to 4, and then up to x is equal to 5. So when our x is equal to, so first I'm really going to put 1 over 5 out. I'm going to factorize it out, 1 over 5 out, and then just take the x minus 3 raised to the power square times e raised to the power tx, and then I'll do the expansion for that. So when our x is equal to 3, I'm going to get 3 minus 3 raised to the power 2 e raised to the power t times what? 3, because we know that our x is here and then our x is 3, right? So when our x is also 4, we are going to get 4 minus 3 all squared times e raised to the power t times 4 plus 5 minus 3 all squared times e raised to the power t times what? 5, right? And then we are just going to expand. 3 minus 3 is 0, so this function, all of it will go to 0, and 4 minus 3 will give us 1. We are going to get e raised to the power 4 t plus 5 minus 3 all squared, we are going to get 4 times e raised to the power what? 5 what? T. That is what you are having here. When you multiply through, we are going to get our moment generating function for this question to 1 over 5 times e raised to the power 4t plus 4 times e raised to the power what? 5t. So that is the moment generating function for what? X, right? Let's go to the next question. The next question says you find the expectation of x and then expectation of what? S squared. That is what the question has asked us to what? Find, right? So the expectation of x, already we know that we will take the moment generating function, take the first derivative, and put our t is equal to 0, right? And then from the question, we had our moment generating function to be 1 over 5 e raised to the power 4t plus 4 e raised to the power 5 what t. That is what we had here, right? So if you take the first derivative of this one, right, if you take the first derivative, we are going to get we are going to differentiate this, so we are going to get 4. So here I'm going to get 4 times e raised to the power 4t, as I have written here. And then we are also going to differentiate the 5t here and multiply it to this one. I'm going to get 20 times e raised to the power at 5t, right? That is what we have here. Okay, that is what we have here. So here we are just going to put our t is equal to 0. Once you put t is equal to 0, we are going to get 1 over 5 bracket will be 4 plus 20, and I'm going to get 24 divided by what? 5, right? So that is what we are going to get here. That will be our answer for the expectation of s. What about expectation of s squared? For expectation of s squared, we are going to take the second derivative of what? The moment generating function. And when you take the second derivative, it means that, you see, we are going to take this function and take the second derivative of it. But already we have the first derivative here to be 1 over 5, 4 times e raised to the power 4t plus 20 times e raised to the power 5t, right? So we are still going to differentiate this. We are not going to take this one and go over again, right? So if you differentiate this, you are going to get 4 multiplied by this, you are going to get 16 e raised to the power 4t plus this one. This is 5. When you differentiate, you are going to get 5, and we are going to get 100 times e raised to the power 5t, right? And put t is equal to 0, we are going to get 116 divided by what? 5, right? So that is that. I'm going to give this question to you as an assignment. Please, my viewers, kindly solve this question and show your answer at the comment section below. Yes, so there are some theorem too that I want to introduce you guys to, for you to really better your understanding on, because some of the questions, they really involve this theorem for you to really understand. Okay, so here we are saying that theorem 1 says that a moment generating function always exists at t is equal to 0 and is equal to what? 1. So that means that if a moment generating function is given to you, right, and then we haven't performed any differentiation on that moment generating function and put t is equal to 0, your answer is always going to be 1, right? So for instance, as it has been proved on the slides, right? So let's say we know that our moment generating function of x is equal to expected of what? E raised to the power t of x. And then if we have this one, and then we are putting our t is equal to 0, are we not going to get expectation of what? E raised to the power 0x. And then this one is going to give us expectation of e raised to the power 0, which will give us expectation of what? 1, which is equal to 1, right? So our answer is 1. So that's what the first theorem is trying to help us to understand. The second theorem too is also trying to help us to understand that if, let's say, a random variable x with a moment generating function, this one, right, and then if y is equal to a of x, it means that we are redefining our y in terms of what? X, x, right? And then we are saying that our y is equal to a of x, where a is constant. Then our moment generating function of y will be equal to mx of what? At, right? Yes. So that means that, you see, we are just going to replace a of x to wherever we see t here, to wherever you see t here. But you see, for moment generating function, the random variable doesn't appear. So in place of the x, you are going to replace that place by what? T. So here, you are going to replace here by what? A of what? T. So how did we got our answer to be this form, right? So let's prove it. So within the proof, we are just saying that for this one, right, we are going to get expectation of e raised to the power t of y. And already we know our y to be what? A times what? X. So that one will come here. We are going to get expectation of e raised to the power t ax. And this one will be equal to expectation, right? We are going to get expectation of e raised to the power at of what? X, right? And then since x is the random variable, our moment generating function will be in the form of what? 80, right? So this is what we are surely going to have. Let's solve an example to better understand. It said, given that x has a moment generating function, of that is equal to 4 divided by 4 minus t, right? Where our t is less than 4, right? Find the moment generating function of y is equal to 2 what? X. So basically, we have our moment generating function here, and that 2x here, that is what I walk you through, right? So here we are going to get my is equal to my of t is equal to expectation of what? E raised to the power 2tx, right? And this one will give us mx of what? 2t, And for mx of what, 2t, m of 2t, right? So that means that anywhere we see t, are going to replace what, 2t, right? So that is what has been done here, right? Anywhere we see t, are going to replace what, 2t, and then that is what we have done here. Okay, yes. And then on the limit that our t is never less than what, 2. So that is the explanation to that. And this, I think, our last theorem that we have on the slides, and then we will bring the uniqueness theorem to an end. The last theorem says that if y is equal to a plus bx, and then mx exists, then our m of y will be equal to e raised to the power t at times ms of what, bt. So let's also prove it. Okay, we have expectation of e raised to the power t bracket open a plus what, bs. So surely it's going to be expectation of what, expectation of e raised to the power ty, right? That is what you are going to get. Expectation of expectation of e raised to the power ty, and then we know our y is equal to what, a plus b of what, x. This is what we have, and then we are going to expand, and we see clearly that this a times t does not include the random variable, so more or less it's going to be constant. So you are going to factorize it out to get e raised to the power at times expectation of e raised to the power b tx. Okay, so that is what you are going to have. And then you see, since x is the random variable, we are going to also replace bt into what, this one, and then once we expand, we are going to get what, this function. Okay, yes. So let's solve example to also better understand it. So when we come here clearly, we know that our 4 here is what, a constant, and we have plus what, 3x. So since 4 is a constant here, right, it's going to come out. So here the a is what, 4, right? So as you can see here, it's constant. So we are going to get e raised to the power 4t, right? And then we are going to put our 3 here to where we see the b. So we are going to get 3t here, right? So when we come here, anywhere we see t, we are going to replace what, 3 what, t, right? So when we come here, this is how things will work out. So you are going to get e raised to the power 4t, bracket will be 4 divided by 4 minus 3t, where t will be less than 4 over what, 3. That will be what, our limit. So that is the end for the uniqueness what, theorem. So this is Statistics and Mathematics YouTube channel. If you haven't subscribed, please kindly subscribe, like, and share, so that this video will get to your friends for them to also watch and be blessed. Thank you. Bye. Have a great day.